All right, everyone. Time for a crash course in binomial expansion. We're diving into Chapter 8. I'm skipping over the first three sections. It's sequences and series. That's stuff that you saw in Integrated Math 1. I know it's been a while. You briefly saw some of that, and realistically, you're not going to need it for calculus. It's not a huge topic, and anything that we would need that deals with sequences and series, we can briefly touch on whenever we need it. So we're going to jump right into the middle of the chapter. We're going to do the last three sections, partly because some of the stuff is definitely needed for calculus and beyond, and some of it's just fun stuff. The next few sections are things that I like to teach, so we'll hit those. Start us out kind of easy. So we're going to look at binomial expansion, which will allow us to raise things to a power, raise sums and differences to a power in a much easier fashion depending on the exponent. So we're starting out with x plus 7 cubed. We have x plus 7 to the third power, which means we're going to write it 3 times, x plus 7 times x plus 7 times x plus 7. That's how we would normally write this. This is how you would do this problem if I were to give it to you right here, right now. And then from here, you would just distribute, right? You would put these two, oops, I erased part of that. We'll put these two parentheses together and multiply them out. Making sure you distribute completely, you would get x squared plus 7x plus a 7x again plus 49. And then don't forget you're also multiplying by this third x plus 7 that's hanging out here. You can make your life a little bit easier. You could combine your like terms, right? And that would give you x squared plus 14x plus 49. And again, don't forget you also have this x plus 7 here. And then from there, you would repeat this process and multiply the x squared plus 49 plus 14x, excuse me, plus 49 times the x plus 7. I'm just going to jump right to the answer. If you distribute all that and combine your like terms, you should get x cubed plus 21x squared plus 147x plus 343. No problem. Right? That shouldn't be anything that we have super duper issues with. That shouldn't be something that we're like, wait a minute, I know, understand that, right? That should be something that we did a long, long time ago back in Integrated 1. So why are we learning something new with this? Well, if that weren't a third power, if that were a 30 power, that would take you a long, long time to do, right? So instead, we have a new method. So I'm going to skip to another slide, and that slide is going to help us redo this problem. So looking at this slide, notice we still have x plus 7 cubed, and I've inserted a picture from your book that deals with this triangle here. And this triangle is called Pascal's triangle. It's named after mathematician Blaise Pascal. He was a French mathematician. And this triangle is created by starting with a 1. So you notice right up top here we have a 1, and then the next row we have a couple of 1s. Then after that, to get every row beyond that, we always start and end with a 1. Notice each of these always starts and ends with a 1. The numbers in between those 1s are created by adding the two numbers above it in the triangle. So this 2 is created by adding 1 plus 1. If we jump down to where this triangle is, that 10 is created because we added 4 plus 6. The other triangle down here, that 21 is created by adding 15 and 6. We could get the 35 in the middle at the bottom by adding the 15 and the 20. That's how Pascal's triangle is created. If we wanted to get the next row, we would start with a 1, we would end with a 1, and then we would just add 1 plus 7, which makes an 8, 7 plus 21 is 28, etc., etc., etc. So that's how each row is created. This will help speed along raising something to a power. The trouble with this is if we needed to raise something to, like I said, the 30th power, we would need to create this triangle all the way out to the 30th row. It would be time-consuming, but doable. It's not like we couldn't do it, but it is something that we would have to do if we were raising to the 30th power. So that could take some time. Thankfully, you could go to a website and type in Pascal's triangle, and you could get any row that you needed. So it's not like the olden days where we would actually have to create them. And there are ways to create without writing Pascal's triangle. There's a way to come up with this 35 right here without doing the whole triangle. It's called doing a combination, and we're going to get to that in a few videos beyond this one. So how does Pascal's triangle help us do x plus 7 to the third power? What that does is allows us to write the coefficients from this triangle. All the coefficients are always the same when you raise something to the third power. All we need to do is find the correct row. Now in Pascal's triangle, this top row is the 0 row. That's important. Then the next row is row 1, row 2, row 3, row 4, etc., etc., etc. So notice when we go to say row 7, the first and last number are always a 1. the second number and the second to last number are 7s, right? That's how you know what row you're on. So you look at the second number in the list or the second to last number in the list. That should be the number of the row that you're on. So let me just get rid of all those again. We're going to focus on row 3 because we're raising something to the third power, and so that would be the row that is a 1, a 3, a 3, and a 1. That tells us the coefficients when we multiply this whole thing out. So we start out with the 1 from Pascal's triangle, and then here's how we get everything else. We take each term that we're adding in here. So we have two terms, right? We have the x and we have the 7. We're going to take that first term, x, and we're going to raise it to the power that we're raising the whole parentheses to, third power. The 7 we're also going to use, we're going to multiply by 7, but instead of starting with the highest power of 3, we'll start with the lowest power of 0. Then we go to the next number in Pascal's triangle. The next number in Pascal's triangle is a 3. We're going to take that 3, and then we're going to do a process to the other two terms. In the last term that we have x to the third, so we're going to drop 1 power from that x and make that x to the second. At the same time, we're going to increase the power on the second term on the 7. We're going to increase that power by 1 and make that 7 to the first. Now it's just a repeating of this process. The next term in Pascal's triangle is a 3 again, and so that's going to be the coefficient of our next term, 3. And then we're going to multiply by x. We're going to decrease the power of x by 1, so that's going to drop it down to x to the first. We're going to increase the power of 7 by 1, and that's going to make it 7 squared. Finally, our last term in Pascal's triangle, the last number is a 1, so we're going to start out with a 1, that's our coefficient. We're going to drop the power of x one more time to bring it down to 0. We're going to increase the power of the 7 one more time to make it 7 cubed. From here, it's just a matter of multiplying all of this out to get our final answer. So we have 1 times x to the third times 7 to the 0. Remember, any number, not anything, any number or anything that stands for a number, a variable, raised to the 0 power is 1. I say any number, not anything, because next year when you get to calculus, we're going to see things like infinity to the 0 power, and that's not necessarily 1. I know that's weird. We'll get there. So for now, every number to the 0 power is 1, so this first term is just x cubed. The next term, we have that 3 is going to multiply the 7 to the first power, so that's going to become 21, and then we have the x squared. The next term, we have 3 times 7 squared. Well, 7 squared is 49, and 49 times 3 is 147, and then we have x to the first power, which I'll just write as x. And then finally, we have 1 times x to the 0. Since x stands for a number, that's also 1. 1 times 7 to the third is 343. And if you notice, this answer that we have here, if I jump back to the last slide, OMG, it's exactly the same answer as we got when we multiplied that whole thing out. Okay, so it's the same answer, it's just a different process. I feel that this process is faster. You may or may not agree, but understand that we only did it to the third power. If we did it to the 12th power, you would clearly see that this can be a much faster process, especially if you don't have to create Pascal's triangle. If Pascal's triangle is already there for you and you just have to go to the 12th row, that does make things go faster. So I've got one more example for us. I want to show us what happens when you have a subtraction sign in between the two terms instead of an addition sign. So we've got x minus 5y to the 4th power. I've got Pascal's triangle over here just as a reference. We're going to go to the 4th row. So remember that 4th row is going to be the row that has the second term in that row being a 4. So that would be 1, 4, 6, 4, 1. That's the row that we're going to use. That row is going to help us expand this. And so just like I did on the last example, we're going to expand this by starting with Pascal's triangle. We start with a 1, multiply by x to the highest power that we're raising it to, 4th power. And then the other term that we have is technically a negative 5y. So we need to take negative 5y and raise it to the 0 power. Then we just repeat this process just like we did before. The next coefficient in Pascal's triangle is a 4. We drop 1 from the x to make it x to the third, and then the negative 5y, not just 5y, the negative 5y increases to a power of 1. Our next coefficient is a 6. X is going to drop a power, x squared. The negative 5y is going to increase by 1 power, and so that'll become negative 5y squared. Our next coefficient is a 4. Drop 1 from the power of x, x to the first, increase the power of our negative 5y, negative 5y to the third. And then finally, the last number in Pascal's triangle is a 1. We'll decrease the power of x one more time to drop it down to x to the 0. We'll increase the power on negative 5y to become negative 5y to the 4th. one thing that you should notice, both in the last example and in this example, if you take any individual term, say this term right here, if you take any individual term and add the powers of your two elements in that term, they should always add up to the power that you started with. So no matter where I go, every single powers, all the powers add up to be 4 every single time. That kind of tells you that you're on the right track. From here, you just have to be careful that you have a negative when you're raising it to those powers. So in this first example, or in the first term, excuse me, we have negative 5y to the 0. Those are all numbers, and so any number to a 0 power is 1. So this is just 1 times x to the 4th, which is x to the 4th. The next term, I have negative 5y to the first power, so that's negative 5y. When I multiply that by 4, I end up with negative 20 x to the 3rd y. For the next term, negative 5y squared, that means negative 5y times negative 5y, that's positive 25y squared. And then when I multiply by the 6, I'll get positive 150. I'll have x squared, and then I'll have y squared. Some of you will punch that up on your calculator. You'll do negative 5 squared, and you'll tell me, oh, Mr. Krieger, my calculator is wrong. It gives me negative 25. Number one, your calculator is never wrong. It's a machine. It doesn't do things incorrectly. You are the human. You do things wrong. When you type negative 5 squared on your calculator, if you want that negative to be squared, it needs to be in parentheses. Parentheses negative 5 squared. If you don't put it in parentheses, the calculator is reading that the 5 is being squared and then being multiplied by negative 1, which gives negative 25. So be very, very careful. It's not your calculator that's making errors. It's your interpretation of how you're entering the information. We make errors. Calculators don't. For the next term, negative 5y cubed, that'll be negative 125y to the 3rd, and then when I multiply by 4, it'll be negative 500. That x is to the first power, and then y cubed. And then finally, we have 1 times x to the 0, which is 1 times negative 5y to the 4th power. That's going to be positive 625y to the 4th power. To me, I know I explained it, but that's still much, much faster than writing out x minus 5y times x minus 5y times x minus 5y times x minus 5y, right? Especially when you go on further, right? Go to the 7th power, Pascal's triangle way faster. That's basically it. So we could do a whole bunch of these different problems. There's a lot of problems in the book. The ones that I would say to give you practice, I would do page 614, problems 25 through 56. I will send that out on Remind. I don't want to put that on the video, mainly because it is copyrighted, and so I don't want to post that up onto the video where it shouldn't be. So I'll take a picture of the pages that we need and send them out on Remind to you, but hopefully you followed my directions and at least took your book home on Friday, so you've got that, so you can start that there. Do as many of those as you want. I know it's a lot. You don't have to do them all. Do them until you know you've got this concept down. So until next time, have a great day and enjoy Pascal's triangle.